Now directly today in this lecture, we'll be directly solving a problem on design of beams. Quickly noting down the problem. It says design a laterally supported beam. Like told earlier, you have for your syllabus is only the design of laterally supported beams and simple supported. Laterally supported beam and simple supported I-beam for a room of size 6 meter into 30 meter. Now this is the width of the room, 6 meter into 30 meter, supporting a RCC slab of 150 mm thick, floor finish of 75 mm thick and live load of 4 kN per square meter and point load of 50 kN at the center of the beam is to be supported. 50 kN at center of the beam and is to be supported. The beam is to be supported on a wall of 200 mm thick. Use steel of grade Fe410. Now for this grade of steel Fe410, your yield strength will be 250 Newton per square mm and ultimate strength Fu will be 410 Newton per square mm. Now since the beam is of the room is of size 6 meter and 30 meter, now the beams are provided on the shorter span. That is, the beams are provided on the 6 meter span at a spacing of 5 meter center to center. So now the span of the beam becomes, the length or the span of the beam becomes 6 meter plus half of the support on either side. The width of the support on either side is 200 mm. So half of 200 on the left side plus half of 200 on the right side. Now totally 6.2 meter. Now this is the span of the beam. Now in this case, what you have to do, you have to calculate the load on the beam. Now whatever your beams are supporting the slabs and floor finish. Your beams are supporting the slab and floor finish. Now you have to calculate what is the load transferred from the slab. What will be the load transferred from the slab to the beams? Now we'll do one by one now. The load calculation. The slab load, the thickness of the slab is given as 0.15 into 25 is the density of RCC slab. 0.15 meter thick is the thickness of the slab into 25 kilonewton per cubic meter is the density of the RCC slab. So therefore the self weight of the slab will be 3.75 kilonewton per square meter. Now coming to the floor finish, FF stands for floor finish, which is the thickness is given as 75 mm, which is 0.075 meters into the density of floor finish is taken as 20. So which you will get it as 1.5 kilonewton per square meters. So next is live load. So the live load which is given as 4 kilonewton per square meter. Now assuming, since we have not taken the designed the beam yet, so assuming the beam self weight as 2 kilonewton per meter. Now the total load will be 3.75 plus 1.5 plus 4 kilonewton per square meter, that is 9.25 kilonewton per square meter. Now this load on the slab, now 9.25 kilonewton per square meter load on the slab will be transferred to the beams. That is, if you take a central beam, this beam will be carrying a load carrying half the load from the slab panel here and half the load from slab panel here. Half the load from slab panel here and half the load from slab panel the other side. Now the slab here is 5 meter and slab on the other side is also 5 meter. That is, this beam will take a load of 2.5 meter slab load on this, and the other side also 2.5 meter slab load on this. That is what. So UDL on the beam will be the total load 9.25 into 5 by 2 plus 5 by 2. So now these are the slab panel on either side. So if it is 4 meter on this side and 6 meter on this side, it will be 4 by 2 and plus 6 by 2. It will be 4 by 2 plus 6 by 2. Now since it is a 5 equal spacing, it will be 5 by 2 and 5 by 2 into 1 meter will show you the length of the beam, per meter length of the beam. Now 46.25 kilonewton per meter. This is the UDL. 46.25 plus 2 kilonewton per meter is the self weight. 2 kilonewton per meter is the self weight. 2 kilonewton per meter is the self weight. Now total UDL on the beam becomes 46.25 plus 2, that is 48.25 kilonewton per meter. That is 48.25 kilonewton per meter. Now drawing that beam. Now, so this is a beam subjected to UDL of, sorry, there is a mistake. It has to be 48.25, not 46.25. This has to be 48.25 kilonewton per meter, and also it is given in the problem that there is a load of 50 kilonewton acting at the center, and span of the beam, which is 6.2 meter, which is already calculated. Now, since it is a simply supported beam, the bending moment will be maximum at the center. So now calculating the maximum bending moment in the beam. So for UDL, we already know the bending moment will be WL square by 8, and for point load, we know the maximum bending moment at the center, which is PL by 4. Small correction here. So this has to be 48.25, not 46.25. So that is WL square by 8, 48.25. Yeah. Coming back to the bending moment. So this is WL square by 8 and this is PL by 4. So summation will give you the maximum bending moment at the center. So now this is bending moment because of the UDL, that is 48.25, and this is bending moment because of the point load. Now this has to be a correction. It has to be 48.25 into L happens to be the span 6.2 square by 8 plus this is point load P is 50 kilonewton, span is 6.2 divided by 4. So when we add up these two, you will be getting the maximum bending moment at the center. Now this is again multiplied by 1.5. Again multiplied by 1.5 to calculate the factored bending moment. This is multiplied by the load factor to calculate the factored bending moment. Yeah. So next one is calculation of shear force. Now shear force will be maximum at the support. Shear force will be maximum at the supports. So now shear force because of UDL is calculated as WL by 2, and shear force because of the point load is calculated as P by 2. Yeah, now again a mistake here. It has to be 48.25 into 6.2 divided by 2 plus 50 by 2. Now this bending, we have calculated these calculation already have done it in your analysis. That is why much discussion is not done here. And maximum shear force is 168.375 kilonewton. Now again multiplying by the load factor 1.5, this will convert it into a factored shear force, which is denoted by VU. So that is 252.56 kilonewton. So now you have to design an I section which is capable of resisting a bending moment of 449 kilonewton meter and a shear force of 252.56 kilonewton meter.